to the second talk. My name is Matthias Rupp from the Fritz Haber, as Angela said, and I'll talk a bit about machine learning, in particular, again, kernel-based machine learning for quantum physics. My talk has essentially 4 parts. I'll start with an introduction, the motivation why I'll present the following. Then I'll talk about the mentioned kernel trick, about kernel-based machine learning. Then a bit more about how to build these models practically, how to choose 3 parameters, for example, how to validate your model. And then I'll give 1 or more examples of predicting properties of materials and molecules. And in the afternoon, we will have a hands-on session where you can try and build these models yourself. So, why machine learning for quantum mechanics? Gabor has already mentioned that there's a problem with the computational requirements of first principles methods. And this shows up in various ways. It shows up in the number of structures like molecules or crystals that you can screen. It shows up in the size of the systems that you can handle. It shows in the simulation times that you can achieve. And it shows in the effects that you can model. I'll be brief here, as we had already heard a bit about this. Here you see some selection of first principles methods, a very accurate method, full configuration, truncated, and then you go down. This is the current gold standard in quantum chemistry, couple cluster. Here's the density functional theory, the current workhorse method that we use. And all the way down here is molecular mechanics, which has no explicit quantum effects whatsoever, but is a lot faster than the highly accurate methods. Don't take these runtimes here very seriously. This is just to give you an idea, nothing exact. Now, I would like to point out one thing. If you use DFT, which has, let's say, cubic runtime in your implementation, then if you double your system size, then you have 2 to the 3, so almost an order of magnitude increase in compute time. That means you can double your system size a few times, and then you'll run into a wall no matter how large the computer is that you run on. Okay, so there is a problem in principle here. So can we be better? Can something be done about this? Well, in general, probably not. You can, of course, improve all these methods, which people do, and which gains you. But maybe in certain situations we can do something new, and that's the machine learning approach. So in high throughput settings, when you want to do a lot of DFT calculations, maybe you want to screen a large database, run a long simulation, compute a very large system, then machine learning can help you to get more out of the compute time that you have. So that's the approach that I'll talk about in the next hour. This is the basic idea. So imagine, let's take the screening example. That's easiest. Let's say you have a large database, a few million molecules. You want to compute the energy of these molecules, but you cannot afford that with a method of your choice. So in this sketch here, the x-axis is some abstract notion of a structure of molecules or materials, a high dimensional, but here only 1D. This is a property like the energy that you want to compute, can be several properties also. And then let's say your database are all the points on this line, and you want to compute the black line here, which would be the reference method, for example, DFT. But you cannot afford that. So what you do is you compute some of these points. These are the reference or training data. And then you use machine learning, the blue dashed line, to interpolate between these points. And that's the idea of this approach. So the question is, of course, to be useful, like Gabor showed, you need to make a very accurate interpolation here. Just one remark, if you have a few points and you connect them, there's no unique solution to this, right? And the functions between these points can do anything. So you have to make an additional assumption. There's no way around that. And we are making, with the type of machine learning models that we use, we are making a smoothness assumption. So we are, in some sense, we are finding the smoothest function through these points. And this turns out goes relatively well with the physics because these potential energy surfaces are usually smooth. Let me not dwell very long on this slide, but just mention that this approach, fitting a machine learning model to ab initio reference calculations for a fast surrogate model, works differently than the usual, for example, force fields that you use, in the sense that you'll have to fit it again if you look at a new problem, but you can always do that, and the fitting is in principle automatizable, so you don't have to spend a lot of time on the fitting of the model to your data. Speed-wise, we are not as fast as a force field. That's very hard to beat, but we are close. Like, think about order of maybe microseconds per prediction, and so we are a lot faster than the underlying reference methods. Well, let's not dwell too long here. So, so what is machine learning? We have seen one example, right? Kernel-based machine learning. In general, it's not so clear what the good definition is. This is the one many people, including me, like. Machine learning is about algorithms whose performance, in some sense, improves the more data they have. And that simply captures this learning from experience metaphor. This is essentially about identifying regularity in data. Either for analysis of the data, think about dimensionality reduction, you have maybe data from a dynamic simulation, you project that down to a few collective variables, and hopefully they will tell you something interesting about your system. Or for prediction, that's what I will talk about today, like estimating the energy of compounds. At the heart, this is the way at least that I use it is always about interpolation in high dimensional spaces, and I think that's a proper way to think about these methods. There are a lot of different problem formulations in machine learning that people try to address. For example, in the same notation that Gabor used almost, X are your inputs, that could be molecules or crystals, and you have n of them, that's your training data, and you have if you have nothing else, you can already look for structure in this data. That's the mentioned dimensionality reduction. But if you have labels attached to your data, for example, the energy, then you can do more. You can do regression. So if your labels are just categorical, like yes, no, conducting, not conducting, then this is classification. If this is a scalar or a few scalars, then this is regression. That is what we will look at here in this talk today as well. And, but you're not limited to that. You can predict structured things. For example, you can try to predict densities, which are 3D objects. So this would be structured output learning. And there are a lot of variants of this. There's semi-supervised learning, where you only have labels for some of the data. There's active learning, where your machine learning model is allowed to say, please, do an ab initio calculation for this molecule. This is what I need to be better. But we'll focus here on regression. I'll not talk about neural networks, so this will be the only slide on them. Not because, it's simply because one has to keep the focus, the scope limited, right? So neural networks are essentially, in one slide, are essentially a collection of simple functions as building blocks. So each of these nodes here is an activation function, like a sigmoidal function, for example. And you have weights, these are the connecting lines here, and then you just sum them up. So by take, like Lego, like building blocks, you take simple functions, you put them together, you get a complicated function. And you can show that if you take enough of them, you can essentially try to approximate an arbitrary function, any function. And in particular, deep neural networks, where you have several of these layers, have become very popular at the moment. Why not use neural networks? Well, you should, if it's the right tool for what you want to do. For example, if you have a lot of data, big data, let's say several million training examples, then maybe a neural network is a good choice. Because for the kernel-based learning that Gabor already showed a bit about, and I will show him a bit more, you have to invert a matrix, the size of which is number of training data, so that becomes a problem if you have a million of them or more. So it's still possible, but you have to go to greater effort to make it possible. Whereas for the neural network, they are built in a way that the training can do that. So it's a good tool, perhaps, if you have that much data. But that's not, for example, what I want to do. I don't want to do big data. I want to do small data. Why? Well, because I want to use these models to save computational time. And each training point is an expensive calculation. Could be a DFT calculation, could be a long simulation that takes maybe a month to finish. You don't want many of these. Okay? So I want to get away with as few training data as possible. And then kernel methods might be a more appropriate choice because you place the basis functions directly on your training data. You get the most out of them in some sense. Okay? So it's not that one or the other approach is better. It's just you need to use the right tool for the right job. And with that, let's get to the next part about kernel-based machine learning. Gabor has already mentioned this, the kernel trick. Let's have a look at it in a bit more detail. So let's start with an example. This is an example of a classification problem. Your inputs x are just one number, one axis here, 1D, and finding and linearly classifying means you find an object of dimension 1 less than, that means 0-dimensional, so a point. So find a point on this line which separates the orange and the blue classes. This is obviously not possible. Why? Because it's a nonlinear problem. And most of the problems that we're dealing with, are interested in, are nonlinear problems. So what to do about it? Well, if we transform this data into a higher dimensional space, for example, by adding a second dimension here, sine of the first one in this case, suddenly we have now a 2D input space, and then we need to find a 1D object, which is a line, that separates the two classes, and well, it's just the x-axis here. So what have we learned from that? By non-linearly transforming the input data into a higher dimensional space, a nonlinear problem might become a linear problem, linearly solvable problem. And that's good because we know how to deal with linear problems. For linear problems, we can do principal component analysis, we can do regression, which I will show here. There are tons of algorithms for linear problems. Okay, so can we just do this like that? No. There's a practical problem here. Your input data, if you, for example, represent materials or molecules, will be high dimensional. We'll have a few hundred dimensions here, maybe a few thousands. Then the nonlinear transformation will not add one more dimension like here in this toy example. It will add maybe quadratically many, cubically many, or maybe will map to an infinite dimensional space here. And that means you don't want to work here explicitly. These are too high dimensional vectors. So, and that's the second part of what is called the kernel trick. There's an observation that there's a class of functions called the kernels, which you compute here in your original input space where it's feasible, where you can compute functions. And they give you the same, this is k of xz here, and they give you the same number as if you would have computed the inner product of the transformed examples in the high dimensional space. So that means these functions allow you to work in this space implicitly by only carrying out calculations here. And that, together with a nonlinear transformation, is called the kernel trick. So why kernels? Why inner products here? What's the point? Well, inner products tell you everything you need to know about geometry of your training data. They give you distance. If you have the inner products, let's say you have a matrix K, which gives you all the inner products between your training data, then this tells you all the distances between your training data and the angles between your training data. So all the geometry of the training points relative to each other. And that's all you need for almost all linear machine learning algorithms. Also good news is that this is a well-characterized class of functions. These are the symmetric positive definite functions. So you can tell both analytically and numerically whether a function is a kernel or not. There are some nice closure properties. So the sum of two kernels is again a kernel, which means you can build new kernels. So, and you can define kernels not only on vectors. You can define kernels on anything that you like. So if, for example, on graphs, like molecular structure graphs, on strings, like DNA sequences, on images, you can define kernels on any objects that you like if you know how to. So that means your algorithms, your machine learning algorithms, can now handle not only vectorial inputs, but also structured inputs. But here I will restrict to approaches where we encode molecules as vectors and put those vectors into vector-based kernels. So how do kernel functions look like? You already saw some of them. The linear kernel is just a line, and you can use it, no surprise, to model linear functions. If you use the linear kernel, which is just the inner product in the original space, no transformations happens. The transformation is the identity, and you get back the original linear algorithm, even formally. You can do that on paper. Now there's the Gaussian kernel that we saw. It's just a Gaussian. These are the basis function forms. And since the Gaussian is a very smooth function, it's infinitely differentiable, you can use it to model very smooth functions. If your functions are less smooth, then perhaps you might wish to use the Laplacian kernel, which is similar but has one norm here and no square. So it has a cusp here. And you can use this one to model less smooth functions like those here. There are a lot of kernels, and you can define your own kernels for your specific application, like the SOAP kernel that Gabor showed. So now how does the regression algorithm look like? Well, in a nutshell, in 1 minute, this is linear regression, rich regression. So let's have a look at the model first. The prediction f of a new, let's say, input, or for example, a molecule x is the sum over the dimensions of your representation of this, of your x, of your input, and each component is weighted by a regression coefficient beta. That's it. Now, how do you get the beta? Well, you solve an optimization problem. You minimize the quadratic error on your training data, and you add a regularization term. Now, this term controls how smooth your predictor, your f, is. You see here, in this case, it's the squared norm of beta, which means the regression coefficients are shrunk towards 0 and each other, which means you will not have very large, almost canceling regression coefficients. And you want that because if your input dimensions of x are very correlated, then you can have these very large, almost canceling coefficients, which will give you basically 0 error on your training data. But for new data, which might be slightly different, they will just give you a very bad prediction, and that's called overfitting, and I'll come back to that in a lot of detail. But this is it. You solve this equation. It's a quadratic equation. So it has a unique global, it's convex, it has a unique global minimum. You take this, take the derivative, set it to 0, write it in matrix form, and you get this expression for beta, an analytic solution. Now, how does the kernel version of this look like? Well, again, let's take a look at the model first. Your prediction f of x is now a sum, but not over the components of x, but over your training data, over all your training points. And on each training point xi, you place a basis function k, like Gabor showed, and weight this by a regression coefficient alpha. But no, the derivation for these alphas is analogous to the linear case. You minimize the quadratic error. Your regularizer now is the norm of your predictor in this high-dimensional space. If you want to know why exactly, if you want to know more about this, I will give you a literature a link at the end of the talk. And Hasty, Tipshirani, and Friedman have some information on this part. But it's essentially the same thing as here. You control the smoothness of your function. Then, again, it's convex. You take the derivative, solve for alpha, and you get this expression. Kernel matrix K, all the pairwise evaluations of the kernel function on your training data, plus a term on the diagonal, the inverse of that, times 1. So here that also tells you the runtime. It's cubic, but only once to train your model, and then you only evaluate it. If your input data changes, you can adapt your solution in less than cubic time, if you're wondering about that. Yeah, and that's kernel-rich regression. This is very close to Gaussian process regression that Gabor used. This is the frequentist version, and Gaussian process regression is the Bayesian version. If you don't know what that means, don't worry. It's something that a fraction of mathematicians cares about, and other people maybe sometimes care less about that. It's very analogous, and the predictions are identical in this case. So this example also, Gabor has already shown, right? So I'll be brief here. Again, it just shows that you have training points, an x and a corresponding y. You place, in this case, a Gaussian basis function on each of them, sum them up, and get your predictor, which is close to the function that you learn. Now, let's have a brief excursion here. Why this form? Why sum over the training data? Where does that come from? Well, it turns out all the kernel learning algorithms, not only regression, support vector machines, kernel principal component analysis, you name it, the solution can always be written in this form. Formally, because there's a family of theorems called representer theorems, which tell you that if you minimize a function like this, a loss function like the quadratic loss and the regularizer, then you always have a solution of this form. The intuition behind this is, although your high-dimensional feature space might even be infinite dimensional, you only have n training points there. And n points will always span only a finite subspace, and the solution will live in this subspace. And that's essentially why this is possible. I also would like to be brief here. This is maybe a very quick example of how you can do something implicitly in a high-dimensional space. So this is centering. If you want to center your input data x in your original space, well, just subtract the mean. That's easy. But how do you center in kernel feature space when you have no explicit access? Well, you have a given kernel k, and the centered kernel k tilde here, well, it's the inner product of the transform phi of x and phi of z, but you subtract the mean in this high-dimensional feature space, so that's 1 over n sum of phi of xi, and here for z. That should, yeah, that's right. And then you can rearrange this term. For example, you can pull out these different parts of the inner product, right? It's these two inner products, phi of x and this, and then minus 1 over n sum, inner product of phi of xi and this. And so you can pull this apart, rearrange it, and if you write in matrix notation, at the end you arrive at an expression like this. So the centered kernel matrix, so the kernel matrix for the centered kernel, is just this transformation of your original kernel. And that's the typical way you proceed. Yeah. Okay, so that was a very brief primer for kernel-based learning. Now let's have a look at how to build models. Let's start with overfitting, because this is maybe the most important thing to keep in mind. This is, again, just an illustration of what is overfitting and how regularization can help. So these are your training points, and you have two functions which both more or less capture these points, but one goes through all of the points exactly, the blue one, and one is smoother. It misses some of the points, but it has less wiggles. So now it might very well be that the orange function is the one that you would like to have, because if your function, like the blue one here, is too crazy in between points, these will be bad predictions, right? If your target function is smooth, otherwise you just need more data. So yeah, let's have a closer look at that. So now in this example, you have trading points in gray and test points or validation points in these empty circles. And the data comes from a quadratic function. Now let's see what happens when we fit. If we fit with a function class that is not complex enough, for example, we use linear kernel here, then we cannot fit this function. We will immediately see this from a high error on the training data. This case is never a problem because you immediately see it. You see your model is bad, okay, I have to do something about it. This corresponds to too strong regularization. If your lambda is too strong, your coefficients are too small, and your Gaussians cannot reach up to model this function. Okay. This, if you choose a proper kernel, proper class of functions, like the quadratic here, then you have low error on training and test data. This is a proper amount of regularization. It allows you to fit the function. This is what we want to have. And now the third thing is what we need to avoid. If you use a too complex class of functions, like cubic, for example, here, polynomials, then you might get a very low error on the training data, lower even than here, but high error on new data. And this is overfitting, and this is less easy to avoid. So this is not enough regularization. If lambda goes to 0, your Gaussians and your Gaussian, let's say you just regularize not enough, then your Gaussians might become like delta functions, and you will reproduce the training points exactly with 0 error and have very high error on any other point. Okay, that's an extreme case of overfitting. So how do we avoid overfitting? Okay, before I come to the practical part, let's take another brief excursion to a generalization of this view. There's a part of machine learning called learning theory, and this can tell you a bit about how your error that you make decomposes. So let's have a look at this. And I put it here because of the complexity of the function class, which we have talked about on the previous slide. So your functions, machine learning, if you build a machine learning model, essentially you pick a function from a class of possible functions. So let's say you have a class of kernels here, you decide for a particular one, you pick one particular model, and that's one point in this function space. So this is a space of machine learning models, basically. Now this is your true solution, A, which will usually be outside of this class. Well, for example, if you predict energies of molecules, well, the solution is a solution to Schrödinger's equation, for example, and this is not a sum of basis functions over your training data. So the function that you want to model will usually be outside of this class F. So if B is the best machine learning model in this class of functions, then you will have this error, which is called the approximation error, because you approximate this true function with something that has a different form. Now, this might be the best machine learning model, but you have to determine it from a finite amount of training data. And that incurs another error, right? You only have a few points. It doesn't mean that you can pick the best parameterization of your machine learning model. So this is the model you can find with your finite training data. And there's another error, E, the estimation error, incurred by that. And there might be others, but let's focus on E and A. So these two, your error will have this part and this part. And this is called in statistics the bias-variance trade-off. So what happens now when you change your function class here? Let's say you allow more complex machine learning functions. Well, your approximation error goes down, but your estimation error gets up because it's harder to find this class. Now, if you reduce the complexity of your functions, you choose simpler functions here, well, your approximation error increases because you'll get further away, even the best solution, from your true function, but the estimation error will go down because it's easier from a smaller class to pick the best model. So this is why it's called a trade-off, bias-variance trade-off. Okay? Okay. Now let's get to validation and how to avoid overfitting. So why validation? Well, for once you want to know how good your model is, right? Before you build a model and then go maybe to some colleague and say, I predicted this molecule to be the best one for your property. Well, maybe make sure that you have picked a good model, right? And you might wish to optimize free parameters. What statistics are we usually looking at to measure the performance of the model? Well, quadratic error, root mean squared error, mean absolute error you often see, the Pearson's squared correlation you often see. Sometimes the maximum error, but be careful with that because it's an extremal statistic, so that can fluctuate a lot. This is all good and well, and you should look at these statistics, but you should do more than that. You should also look at the distribution of your error. So if you build a model and you compute the errors on a validation set, just look at a histogram of the errors. Do a bit more than just summary statistics. Oh, and of course, you should always have a learning curve like Gabor showed, where you plot the error versus the size of the training set. That you should also always report. Now, on what do we compute these measures? Well, there's basically just one very simple rule, which I've here called golden rule of validation. It's never use data for validation that you have used to build your model. That's basically the only rule you have to follow. But sometimes it can be a bit complicated to follow it. So if you don't do that, you will get what we saw 2 slides previous, right? If you report errors on data that you have used in training, you can basically, these can be arbitrarily small, but they tell you nothing about data, about the error on future data, on new data, which is the interesting part, right? So please never do that. If you build a model, compute the error on the training data and submit that, you should be banned from the journal, and please never do that again. So keep that in mind, okay? Don't do that. Just follow this rule. So how to do it? Well, if you have enough data, it's very easy. You take your data, maybe you have a set of 10,000 reference calculations, you take out part of it, you can argue how you do it. If you can do it randomly, that's okay. You can do something else. And that you take, let's say, 1,000 out. That's your validation data. You never look at that again. You build your model on the remaining 1,000 points, do everything that you want. And when you're convinced that it's a good model, then you take your 1,000 points, your validation set, and compute the error on this set. And that's it. That's the easiest thing to do, and it makes sure you don't do anything wrong. Now, what happens if you don't have so much data? Well, then you can do statistical validation procedures. You will see that sometimes the most popular one here is the k-fold cross-validation. Let's say, for example, that you have only 82 data points. There's maybe not so much you can do with 82 data points, right? So you can certainly not set out aside half of it. That takes away half of your data, right? So what you can do in this case, for example, is you take out one single point, your validation point, you build your model on the remaining 81 points, and then you predict this one point that you took out. Okay, fine, you get the error on this single point. And then you repeat this procedure for all the remaining points. Let's leave one out, cross-validation. That is, of course, a lot more effort, clearly, but it gives you, for each training point, a prediction error that is derived from a model that has never seen this point during training. So you're okay with the rule, and this is a good statistic to report. But you should realize that this is really only necessary if you don't have enough data. Do I have? Okay. What happens if you? Let's do it on the next slide. So if your model will usually have 3 parameters. So for example, the length scale of your Gaussian kernel is a free parameter or hyperparameter. The regularization strength is another free parameter. You might have a lot more free parameters. So one way is to set them based on physics. This is what Gabor has shown, so I'll not go into that. If you have a good, or maybe let's do one example. If you remember for example, the error was clear, I think, from Gabor's talk. Let's say you have the Gaussian kernel, and you say, okay, I don't want to optimize it, I just want to set it to some meaningful value. What do? Well, if you remember the formula, it's exponential of minus, and then distance between your input space points divided by this length scale, essentially. Well, numerator and denominator have to be roughly on the same scale, otherwise you will get only zeros or ones, which is not meaningful. So you set them to be roughly equal, and then you compute all these distances between your input points, and you say, okay, now I know that my length scale has to be roughly on this order, and just set it to that value. That's a heuristic. That's just a heuristic, but it basically says my input space has this scale, so I'll approximately set the value. This will, of course, not give you the best performance, but if you do it right, it will give you quite reasonable performance without having to optimize a lot. The alternative is to optimize the 3 parameters. There are various ways how you can do it. You can compute, for example, the log likelihood of your model, and then you get a non-convex optimization problem you have to solve. If you have just a few 3 parameters, like maybe 2 here, length scale and regularization strength, then you can do it with a grid search, for example. So, and I bring that up here in the context of validation to give you an example of where you need to do a bit more than just setting out a validation set in the beginning. So let's have a look at this. You take some possible values for the length scale, maybe on a logarithmic grid, and for the lambda as well. And then for each combination, you want to estimate how good your model is and then choose the best combination. So how do you do that if you also want to know how good your model is in general? Well, you start, let's say, with these 10,000 training points you have. You set aside 1,000 randomly sampled ones for validation later. You're left with 9,000. Now, to optimize the 3 parameters, again, you split these 9,000, so kind of an inner training and validation set, if you want, let's say into 8,000 and 1,000. And then for each of the possible combinations of your 3 parameters, you train on the 8,000, estimate performance on the inner 1,000 validation points, and then you pick the combination which performed best, and then you train a model on the 9,000, on the original training set, with these parameter settings, and then only you have your final model, and you predict the original 1,000 validation points you set out in the beginning. That way you make sure that the performance you report was measured only on points that the model did never see during training. Still, you were able to, in this inner loop, basically, to optimize your parameters from the data. Of course, that will only work if you don't have the grid search only works if you have a few 3 parameters. If you have more, then you can still do something like this, but you have to be a bit more clever. For example, you could start with the heuristic from the previous slide and then do something like a discrete gradient descent, for example. Then you don't have to compute on all the grid, but you focus on the area where the performance is good. That way you can handle I didn't try how far this goes, but a few, let's say half a dozen parameters was no problem. I guess a few more are good as well. And if you put work into this, you can maybe, I think, get away with a lot more free parameters. Okay, how much time? Yeah, maybe let's have one or two examples again with this validation rule to see how this works. So, okay, the plain biggest mistake I already said, never train on all the data and report that error, don't do that. Now what about if you need to center your data? If you want to subtract the mean of your inputs x? Well, if you just compute the mean over all your data, subtract it and then split the data, that's wrong. Because the centering is part of the model building and may not be done on your validation data. So the correct way is split the data first, then compute the mean on the training set, center there, train, and then when you have your model, you can subtract the mean from the training data from your validation points and predict them. Okay? So order is important here. And this is basically the same thing as on the previous slide. If you do an inner validation to optimize your free parameters, you need always to be careful with the splitting. Set aside your validation set, never touch it, do whatever you want on the training data, another round of splitting if you want, or another one, but then only in the end predict the validation set. Holds for cross-validation as well. It's called, what was it called? Nested cross-validation. If you hear that term, it just means that. Okay, in the last remaining 10 minutes, let's get to an example of property prediction. So what did we do with this methodology that I presented? Many people have done by now in the last years a lot of studies with this approach, and yeah, you can see examples here. You will hear about this one later by Luca or someone from his group. It was applied in inside density functional theory, for orbital free DFT, in transition state theory, many examples. Gabo showed some of them. I would like to show you interpolation across chemistry, changes in the structure of compounds. So this is the screening example from the very beginning. So what's the problem? The problem is there are a lot of molecules and a lot of materials, and you cannot compute all of them. Okay? This is because this is a combinatorial problem, right? For molecules, this is essentially graph theory. You can combine the different building blocks into larger and larger, more and more molecules. And for materials, it's group theory, essentially. But the point is, there's a combinatorially large space here. And if you want to screen that, well, you have to come up with a clever solution like the machine learning approach. So this sketch is supposed to show this. So let's say this is the potential energy surface of a single system, like one molecule, for example, right? You know some of your training points, and you're hoping that your machine learning model can exploit the information here to help you predict a new point on this surface. And now what we are doing when we are predicting across different molecules, different materials, is saying, okay, we have other potential surfaces, and we are hoping that the information we learned on this surface will also help us in predicting the energy for this different surface. Maybe we need 1 or 2 points here, but yeah. So this is the idea. Our first study in this field is from 2011, where we tried this first, so that's why I'm showing this. We had 7,000 small, tiny organic molecules. We relaxed them to the ground state with a hybrid functional DFT, calculate their atomization energy, and then simply ask the question, can we use machine learning to accurately interpolate between these different molecules? And the answer was yes. Here's the scatter plot of DFT versus predicted energy. We got an error of about 10 kcal per mole, which at the time was good, but of course now is far from the state of the art. Today you would expect a good model to have an error of, let's say, half a kcal per mole, or a bit less maybe. Here's the learning curve that I mentioned, right? Size of the training set, the error. Here's the mean absolute error and the root mean squared error. And the dashed and dotted lines are what the learning theory from one of the previous slides tells us how the error should decay from theory asymptotically, and you see that it quite nicely does so. Okay. Now the most important part in this model is kernel-rich regression, like I showed. The most important part is how you represent your atomistic systems, like these molecules, to the regression. And Gabor has already presented a sophisticated model, so I will be brief here. At the time, we used a very simple model. We called this a Coulomb matrix. So what we did is basically take a molecule and then create an atom-by-atom matrix. And each element is the sum of the nuclear charge Zi, Zj divided by the distance between these molecules. So extremely simple, Coulomb terms. Has nothing to do with using Coulomb's law to explain anything. It's just a representation for interpolation, nothing else in this context. So, and that gave you the 10 kcal per mole performance that you saw before. And now then, in the following years, we understood better what the problems and requirements are. For example, this representation has discontinuities, and Gabor already mentioned that this is a bad thing. For example, there's no clear order here, right? It's atom by atom, but atoms in which order? So we sort that. But if you sort, and then you change one of the atoms, move it through the molecule, then the sorting at some point will flip. It will change. And that's a discontinuous jump in matrix space, and that's bad. So by now, today, we have better representations. Gabor soap is one of them. We have also a new one called many-body tensor representation, which I have not presented today in this hour due to time constraints, but you can look it up on the archive. And that gives and you can also use it in the tutorial if you want to, and that gives you a much better performance. So then in the following time, we did more studies. We played with the representation. We looked at more properties, homo-lumo gap, polarizabilities. We looked at more molecules. We set up a database of 100,000 molecules. So we developed this approach further, essentially. We also looked at some neural networks, of course. We tried different variants. So this is more in the spirit of what Gabor showed. So far in the previous examples, we had encoded the whole molecule or whole material in as a matrix or a tensor. But if your system gets too large, that might be a bad idea. Because imagine a very large chain of atoms that can do so many things, and it might be hard to learn that. So you would like, in some cases, to exploit locality. And this is this finite cutoff idea. So you take, instead of representing the whole molecule, you take an atom, a finite environment around it, and predict an atomic contribution to the energy. This gives you, on the one hand, scalability. So you can do arbitrarily large systems, basically, with that. Because you ever only train on small environments, and your prediction is, let's say, constant time, if the training set size is a constant, and then you just have linear prediction time for the molecule. But on the other hand, it costs you, because the energy is not a function of additive atomic contributions. So you cannot model all systems using this approach. So it's a trade-off again, and you have to choose the right approach for the right problem. So let me summarize what I've shown. I've shown you, I've said that machine learning is an approach to find regularity in data that is used mostly either to analyze the data or to predict new data. And these algorithms from this field have in common that they improve the more data you have. Then I showed you the kernel trick, so how kernel-based machine learning works. It had two parts, the implicit, the transformation to a high-dimensional space, and then implicitly working there using the kernel functions. Showed you kernel-rich regression as an example. Then when you build your models, always remember, be careful when you validate them. Only report error on data that was never used during training. And finally, I showed you an example of what to do with that, the interpolation of energies of organic molecules. And then I would like to point you to this. We will have a hands-on session in the afternoon, which is essentially based on this publication here, which you can download. Here you will get a bit more detailed explanation of what I covered today in this hour and a bit more. So you can read more here if you want to. And you can find, if you want to play around more, you can find data sets here. And with that, I would like to thank you for your attention.